In this video, we will be talking about radioactivity. And the very fundamental question is, what is radioactivity? And then we would like to see the dependence of this radioactivity on temperature and pressure. So let's try to understand this phenomenon. And what is radioactivity is basically it's a phenomenon of spontaneous emission of radiation. That could be the proper statement: spontaneous emission of radiation by a heavy element, uh, and, uh, and this kind of the kind of emission that's spontaneous in nature. This phenomenon is referred as radioactivity, and the elements that undergo this spontaneous emission of radiation, we call them as radioactive elements. We call them as radioactive elements. Now, this radioactivity, it was discovered by it was discovered by it was basically discovered accidentally by Antonio Henry Becquerel, and and what he noted that uranium with atomic number 92, it gave out some invisible rays or radiations that could penetrate through several thick black papers, and could affect the photographic plate. They could affect this photographic plate, and that was placed in front of these radioactive elements, in front of these uranium atoms, uranium elements, and they could penetrate these black papers and affect the the papers, affect the photographic plate that would have been placed behind these plain sheets, the black sheets. And the same phenomenon was confirmed several months later. I think this Henry Becquerel, uh, it was in 1896, and after several months later, Perry Curie and Marie Curie, uh, they named these penetrating rays as Becquerel rays. See, they call them Becquerel rays. Okay, and 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 Curie was able to show that uranium ores, the ores that contain this uranium, they contain traces of polonium. They contain traces of polonium and radium, and these elements were much more radioactive than that of uranium. So, for example, the these elements that were discovered by Perry Curie and Marie Curie, they were more radioactive than that of what was observed by Antonio Becquerel when he was investigating. Accidentally, what he found is some radiation coming out of uranium and affecting the photographic plate. Now, what is the cause of this radioactivity? As we have talked about, that we have nuclei that are unstable. That means instability of heavy nucleuses. So we have instability of heavy nucleuses that causes this radioactivity. And and the next important reason is the binding energy per nucleon that we have talked about. Now, this binding energy per nucleon, it slowly goes on decreasing. If we go rightly back to the binding energy curve, it goes on decreasing with increasing mass number. So this binding energy per nucleon is less for these elements. So the elements whose mass numbers are greater than 140, uh, we find that these nucleuses are not stable, and heavy nuclei have large number of protons, and there is electrostatic repulsion, and this electrostatic repulsion between the protons badly affects the nuclear binding energy that we have between the nucleons, and thereby makes the heavy nucleus unstable. Now, what is the possible effect of the environmental conditions to these radioactive materials? Is if we see that it was observed basically that the physical conditions like temperature and pressure, they do not affect radioactivity. They don't affect it. They have no influence on it. Now, if we try to see, have a small demonstration of these Becquerel rays, we have we have we have a situation. If we can drag out a situation for the sake of simple understanding, what we have, the mystery about these Becquerel rays, it was experimentally investigated by Rutherford and his associated. And a simple experiment demonstrating this can be seen here, which I'm trying to draw. And we have a sample of a radioactive element. So here we have radioactive element, and this element is placed in a cavity made of block of lead. Okay, it's made of a block of lead, and uh, when oppositely charged plates, we have two plates. Say this is positive plate, this is a negative plate. When these plates are placed at the sides of the beam of the beam of rays, some of the rays are deflected to the left, and some of the rays are deflected to the right, and some of the rays are undeflected. Very simple experiment, can be understood in a simple way what's going on here. So some of the rays go to the left, some to the right, and some are not deflected at all. And a magnetic field around the beam of these rays shows the same effect. If we take the same experiment and place a horseshoe magnet and have the same sample, and the same kind of behavior is observed there, where we have the alpha rays, and we have the rays going in opposite direction, and we have the rays that are undeflected. So the rays that are deflected to the left in this case, that are deflected to the left, they are positively charged, and they are known as alpha rays. And the rays that hit the positive charge of this plate, they are known as beta rays. And the rays that are undeflected, they don't have any impact of the direction of electric field, they are called as gamma rays. Okay, so these rays, which are neither deflected by either of the charges, they are gamma rays, which we call as gamma ray photons. Now, if we seek this experiment, if we try to explain this simple thing, that alpha rays, what happens in this case is that an alpha particle, which is basically helium 4 and 2, it has two protons and two neutrons. When two electrons orbiting around this nucleus of atom are knocked out, you knock out two electrons out of this helium, then we have a doubly ionized helium atom, which is known as alpha particle. Get rid of two electrons, and the remaining thing that we have is alpha particle. Okay, and so we have the distinguishing. We have the distinguishing of some parent nucleus, say X, A, and Z. So what happens here is we have a daughter nucleus, and what happens to the mass number? It goes down by 4. What happens to the atomic number? It goes down by 2. And what we get is He4 and 2. So this is what we obtain when we have alpha decay, when we have the production of alpha rays from the sample. Now, the daughter nuclei, which may or may not be radioactive in nature, so it depends on the situation. It can be radioactive in nature, it may not be radioactive in nature. Now, to move on from here, is beta particles. And what are these beta particles? They are fast moving electrons. And this beta decay, from reaction point of view, now what we have is beta decay. Okay, so what we have, if we take a parent, nucleus, in this case, what we have is a daughter nuclei as X, A, and Z minus 1, plus we have a beta particle, so and we have an entry neutrino. Now, it may be noted here that this antineutrino, they do not exist inside the nucleus. They don't exist inside the nucleus, but they are created at the time of emission of beta particles. So they are created, they are a consequence of that decay, gives birth to these antineutrinos. And then talking about the gamma rays, what we have is gamma rays. And what are they? They are high energy electromagnetic rays, or you can call them high energy packets of electromagnetic radiation, also called as photons. And they do not have any charge, and their rest mass is zero. Their rest mass is zero. So to write down a nuclear decay for an atom, for a nucleus, say A and Z, this assuming this to be in excited state originally, and this goes back to its original state and emits a gamma ray particle. So if you have a nucleus in excited state, it will undergo gamma decay and it will come back to its ground state. So this is my excited state, and this is the ground state. And talking about this antineutrino that we have, it's an antiparticle of neutrino, and the mass of this neutrino is zero. The charge on this neutrino is zero. It is a natural particle. And neutrinos and antineutrinos, they are emitted to conserve the energy and momentum during the decay process. And conversion of proton into a neutron, we have positron. What we said in this case, we have electron. If we have a conversion of a proton into neutron, here we have conversion of neutron into a proton. In that case, we have the antiparticle of electron, what's known as positron. And in the next video, I'll be just talking about the properties of these particles, the properties of these rays known as alpha particles, beta particles, and gamma particles.